Welcome back to Introduction to Computational Fluid Dynamics. I'm your professor, Steve Miller. Today we'll be talking about numerics, in particular time discretization. We've spent much of this section looking at different ways to discretize the equations of motion, and these are focused more so on space. What we haven't talked about is how to advance equations in time or find particular solutions which are steady. This is the subject of this class. In the previous class, we looked at two major methods. The first is the finite element method. This is the idea of where we discretize a domain, break it up into small elements, and estimate the basis function and minimize its coefficients of the residual so that we might find a solution. These form the so-called weak solutions of the equations of motion. Then we looked at the formulation of the finite volume method, which is perhaps the most physical method for many people. This, of course, it uses an integral form, and it strictly conserves all the variables of that we're interested in. This approximates and equalizes fluxes across the domain in a steady problem, and, of course, directly accounts for them through the boundary conditions. This is also a very geometric approach and very algorithmic. I think many people appreciate its simplicity. However, there are certain disadvantages. For example, the finite volume method is usually restricted to very low order. The finite element method can reach very high order of accuracy with just the increase of the polynomial basis function. Today we're going to start talking about the whole concept again of steady versus unsteady flows. We'll try and define this clearly, especially because for a turbulent flow, which by definition is unsteady, could be handled in a steady way, given some certain statistical assumptions. These are very simple, and this is what mainly the types of flows we'll be looking at in this class. Unsteady flows, of course, are ones which are time invariant. We'll then look at the time integration approaches. That is, how do we march a solution in time? How do we calculate the time evolving flow? That's for the unsteady case. We'll be looking at, in particular, at the partial derivative of the variables with respect to time. And we can assume that we can use any of the types of discretization approaches we previously talked about. Then finally, we'll talk about the differences between implicit and explicit schemes. We'll look at a number of schemes in this class, ones that maybe are very classical and very popular, and also ones that are used today in almost all CFD codes. In the next class, of course, we'll be talking about some more advanced schemes for these types of ideas. Let's now turn our attention to the whole concept of steady versus unsteady flows. It's a major decision most people need to make when they're running a solver. Many contemporary solvers can do both. Some research solvers may only do one or the other. Pretty much any commercial solver you have today will be able to calculate a steady flow or an unsteady flow. It's just as simple as clicking a button of a mouse. In the solvers we're using, if you edit, say, text files that are input to the solver, it's completely possible to change this with just a few lines of the text file. Either way, all the boundary conditions and discretization remains the same. The only change is the solver and how it's approaching the solution. We'll define a steady flow as one that is statistically stationary, that is for a turbulent flow, and of course there are exceptions to this, of the governing equations without the so-called partial time derivatives. So it's very much possible to have a turbulent flow that is not transient, and we could treat it as statistically stationary. If the flow is fully developed and moving along, and it's not changing with time, we can try and find the so-called statistically stationary solution. The statistically stationary solution only means that the statistics of the flow, like say energies or statistical quantities or higher order moments of statistics, are not changing with time. Still, this is an assumption, and of course no flow truly has these characteristics, but measurements in labs where we find these statistics match extremely well with the predictions of a statistically stationary flow solver. If it's a laminar flow and it's steady, then you can view it as a truly steady flow, that no velocity fluctuations or any perturbations of pressures or temperatures or density are occurring in the flow. The second major case, of course, is the unsteady flows, which are temporally evolving, and these might be fully resolved in time, and we must fully resolve those time derivatives of every field variable: densities, velocities, pressures, and temperatures. In this particular slide, I've shown two examples of the so-called steady and unsteady flows. In the lower left, we've shown one particular airfoil, the S809 airfoil. And we've shown contours of Mach number, which are shown here by my cursor, from 0.005 to 1.335 in the red. You can see that a shock wave has formed above the airfoil. This is clearly a transonic case. The approximate incoming Mach number is about 0.8, just approximately, because you can see that's green relatively everywhere in the undisturbed median. Around the airfoil, a normal shock forms on the upper side of the airfoil. It's very possible that in reality that this normal shock is moving back and forth. So in fact, we are actually forcing through the study solver to find it some position. In some sense, it might be viewed as some sort of statistically derived position as we drive that solution and to a steady state. It's not really the physical solution itself. This might not be the best choice for a study solver, but yet it's often done and is a benchmark case. On the lower right, we simply are looking at an unsteady case of a similar airfoil at approximately the same Mach number, higher angle of attack, and with its flap at a deployed state. You can see in this unsteady case, almost all the flow on the upper and lower side of the airfoil it looks relatively steady for these contours, but behind the airfoil we see some shedding. And of course there's an wake. It looks like a rather laminar wake. Nonetheless, for this particular case, the flow is unsteady in that we are getting a temporally evolving wake behind the airfoil. If you care about unsteady loads on this particular airfoil, you would absolutely have to do an unsteady simulation. That means you're accounting for the partial derivatives of the equations of motion with respect to time. You're not canceling it out like in many of your earlier classes. Another point to make is that you can also treat unsteady flow fields like this in the steady sense. In fact, you can pretty much take any type of flow field and make the steady assumption. That is the statistically stationary assumption. By doing this, you'll be driving this flow field to its perhaps time average value, or a base flow, or temporary average base flow. There'll be some average state about these fluctuations that we reach. For example, if you have a fluctuating signal and you take the average of it, the time average, you would have a single value. That's the particular value that you would typically find or you can think of for steady simulations. This is actually much more complicated, and there's a little bit of nuances to this that you should be aware of particular solvers and methodologies. You may not be finding a time average after all, but some other type of averaging quantity. Perhaps it's a mass average, which is very typical in steady compressible turbulent solvers. For now, let's look at the time integration approaches. That are approaches that are trying to resolve the flow and take it from one state in time to the next. That is, it's temporally evolving. We have previously discretized the equations of motion with much effort in space mainly, with the volumetric, the elemental, and finite difference approaches. We can, of course, also do this for the partial time derivatives. We can apply similar methods to time derivatives, but it might take some special consideration because we have to know about multiple time levels, which isn't always the case for spatial discretizations. Now, the derivatives in the time domain are sometimes called one-sided. That means because the state of the future is unknown. Imagine we have our central finite difference stencil. If we apply it at, say, time t, we would also need to know times t minus 1 and t plus 1, for an example. That doesn't mean that delta time step is necessarily 1 second. I'm just talking about the time levels. Just like we go from grid point I minus 1 to grid point I to grid point I plus 1, we might go from time level n minus 1 to time level n, the current time, to the future time n plus 1. We could apply a finite difference stencil to time just like we do in space, but unfortunately that would require us to know something about the future, which we don't yet. So these methods are possible, and that's the difference between the so-called explicit and implicit methods. For now, know that derivatives are sometimes one-sided in that the stencil will be biased towards the time of the past versus the time of the future. For example, we might use our stencil to discretize the partial derivative with respect to time as n minus 1 and n. So we would have a first order finite difference. We'll show this mathematics in a few minutes. Just like we showed in the finite difference approach, you might imagine it is also possible to calculate higher order derivatives by simply using higher order truncations of the Taylor expansions to form one-sided finite difference equations. Of course, this would require more time levels. For example, a second-order time-accurate scheme might require 3 solutions to advance in time. The solution in all space at n-2, n-1, and the current time n to advance in a future time. What does this mean? The higher order schemes will use and require more information about the spatial domain at many more times to achieve higher and higher order. Let's talk about one of the most straightforward and simple ways to integrate in time. This is the so-called explicit time integration. Explicit time integration means that the solution at the future time is found using only knowledge of the present and past. This is probably the most obvious and physical way to integrate in time. It does have certain disadvantages which restrict the stability of the solver. For example, if we try to go forward too much in time, then the solver will become unstable from the current time. For example, I might go from, say, the current time to 10 seconds in the future. That's probably very large for a computational fluid dynamics solver. Typical time steps in aerospace might go from the current time to maybe 10 to the negative third or fourth seconds in the future, and that's a conservative estimate. Now, let's illustrate the explicit time integration method through one particular example. Let's imagine that we have the continuity equation, which is compressible in 2 dimensions, written in its conservation form, which is in the middle of the page. That's partial rho, partial t, that's the partial derivative with respect to time, plus partial rho u, partial x, plus partial rho v, partial y is 0. We will approximate the second and third terms with finite differencing, and we'll try and approximate the first term with respect to time and finite differencing. Let's directly insert all 3 finite difference approximations into this equation and find what we have. We will choose central differencing for this scheme in space and first order forward differencing in time. This is an explicit time method, marching method, and a centralized finite second order scheme for space. Let's look at the second term of partial rho u, partial x first. You'll see we have, and let's read it together, rho u at I plus 1 of j to the n minus rho u of I minus 1 j sup n, superscript n subscript I plus 1 j, all over 2 delta x. The denominator remains the same. It is twice the grid point spacing. We derived the central stencil a few classes ago. In the numerator, we have the same quantities. We are taking the difference between the grid point at I plus 1 and subtracting it from the grid point and I minus 1 while holding j constant for a particular grid point ij. You'll see the superscript now has an n. This is not to the power n at all. N is the current time level. We are usually in our CFD notation at time level n. So we know the solution at time level n. We have done the same thing for the partial derivative in the y direction for the third term. We've also added higher order terms. You can see in space we're second order accurate, and you'll see in a minute that in time we're first order accurate. Now we've discretized the second and third term, which are the spatial variables. We need to discretize the first variable still. So we want to use an explicit scheme, and we'll use Eulers' explicit scheme. Here, instead of a delta x, we'll write a delta t. So it's still a finite difference, but instead of the spatial direction, we're going in the temporal direction. It is, of course, of rho, because that's what appears in the numerator. We're trying to find the partial derivative with respect to rho, so we put rho in the numerator. And it will keep the grid point constant, ij. So from one grid point in the current time n to the next time, we are not moving around our grid point because we're taking the finite difference in the temporal direction. Take a minute and think about that. It might be useful to draw it on a paper. Maybe write a grid in 2 dimensions and then write another time level at n plus 1. Now we write the new time level. The current time level is n, and the new time level is n plus 1. So the numerator is, of course, the difference between the future density and the current density at location ij from times n plus 1 to n. Recall, we know the density at time n. In fact, we know everything in this equation now except rho of n plus 1. We can, of course, solve it. Now, you might say, oh, Professor Miller, I don't know the velocities, for example. Well, you do, because they are value n. So we assume that we know all field variables, densities, velocities, pressure, temperature, etc., at time level n and all previous time levels that we desire, because we store them in the computer. If we're starting a simulation, it would be the initial condition, n equals 0 at time equals 0, for instance. Now we can have and close an explicit system of equations to advance in time. I could solve this whole equation for rho of ij n plus 1 and have my closed form equation. This is an explicit time integration because I'm able to find a closed form solution of n plus 1. Let's show these steps now. I have used the notation sup n to denote the iteration. Remember, n represents the current time and n plus 1 represents the new time, and iteration n plus 1 or n minus 1, etc. In fact, we could advance to n plus 2, n plus 3, n plus 4, etc., and just keep incrementing our n's from one time level to the next. So if we solve from the previous equation for rho of ij at n plus 1, we'll find the following equation. We simply move the spatial terms to the right-hand side, multiply both sides by delta t, and add a rho ij of sup n to both sides, and we'll isolate rho of ij n plus 1. That's what this equation is here. We have found what we call the forward Euler time differencing scheme, and I apologize, this is backward. It should be forward here. That's a typo. We call this a first-order accurate temporal method because, of course, the discretization is first order in time, as you see in the lower right corner. We have found a first-order scheme in time, as you see in the discretization with delta t. It is easy to apply this scheme, this explicit Euler explicit time integration schemes, to almost all sets of partial differential equations, but unfortunately it's almost not useful for some sets of problems because the stability of the scheme is marginal. It restricts us to taking extremely small time steps, which could be computationally expensive. Since it's only a first-order accurate scheme and the spatial discretization is second order, the whole scheme will result and be reduced to a first-order scheme. That is, everywhere in the domain we will always have a first-order solution because we've used a first-order scheme in part of the methodology. So remember, your CFD scheme will always revert to the lowest order scheme of its discretization. In this case, even though we've done the work of doing second-order discretization, the whole scheme will be first-order in practice. And we can have numerical ways to show this. Of course, the discretization should be chosen based on the physics of the problem. So some problems, of course, may not work very well with these types of discretizations, and other ones will work very well. So it depends not only on the CFD, of course, but of the particular physics of the problem. The stability and convergence of this scheme are not guaranteed. That means we can choose what the delta t is in our scheme. Delta x and delta y are likely fixed because they're a function of the computational domain. They're not easy to change. But what is very easy to change in the computer, of course, is to change delta t. We can choose how fast we march in time. We'll talk about the stability of this choice in a few minutes. Of course, these low accuracy methods do not give very good results, especially so on coarse grids. You might now ask, what happens if I increase the order of accuracy of my time integration scheme and keep it as an explicit method? I would replace the time derivative, perhaps, it's my choice, with some kind of second-order finite difference in time. That's what we've done for the continuity equation here in this slide in the first line. The second and third terms, which discretize space, are still second order, and we preserve them from the previous case. We let the time level remain at n. Now we rediscretize the first term, partial rho, partial t, and we write 3 rho ij of n plus 1 minus 4 rho ij of n plus rho ij of n minus 1, all over delta t. Well, you can see that the coefficients are a little bit different than the standard second-order central difference. It's been biased. Remember, we have placed coefficients, and we've talked about their how they can be chosen based on some optimization scheme or solver. Remember, there's actually an infinite number of choices for these particular coefficients, especially when you go to higher-order schemes. Here, you can see now with this particular scheme, which is importance of how we found it is not too important at this point, is now second order. And it also contains the time levels n plus 1, n, and n minus 1. You can notice by going from first to second order, now we have 3 time levels. To solve for rho of n plus 1 is still simple, because we assume we know time and levels, all the information at time of n and n minus 1, we can now explicitly solve for 3 rho ij of n plus 1, and that's what you'll see at this bottom equation. You'll see rho of ij of n plus 1 is now a function of all other variables at time n and n minus 1. You can see there's a problem with this approach now, in that now we are required to store the entire computational fluid dynamics solutions, not only at the current time, but the previous time. Of course, this is easy to program and have in a computer, but you can imagine for large three-dimensional grids, it's very computationally expensive because of the amount of memory used. There's ways to optimize this in the computer and the algorithm save memory, but of course, you're still going to have to pay the price at some point. There's ways to get around this, and they're usually called compact approaches. We'll mention these in the class later. Remember, everything on the right-hand side is known for the explicit approaches, and there are complicated algorithms to have even higher accuracies with limited time levels. And these might be called here the so-called Lax-Wendroff approach and McCormick approach. They're both also second order in time with 2 time levels instead of 3. That's actually fascinating. So you only would have the previous time level and the future time level. That's much more compact temporally, but still, if we increase the order of these schemes, generally you'll see that we have to pay the price of using more memory and more computational power, but we get the advantage of higher order of accuracy and maybe even larger time steps and better stability. Let's now look at one of the most important developments in computational fluid dynamics for highly accurate unsteady solvers. This represents the workhorse solver in research and CFD. It and its variants have revolutionized the field. If you're doing an unsteady method and you want high order of accuracy and very efficient time marching algorithms, then you might choose this method. The method is named after its authors. It was a professor and student, of course. It's the RungeKutta Method. Here, let's try and explain the method, and you'll see its power. We would introduce the so-called definition of the local truncation error. The local truncation error looks very much like the general forms of the explicit equations we just developed. For example, of y of t plus delta t minus y of t over delta t. This is a general form of a differential equation where we are discretizing in time with explicit Euler scheme of first order, minus a function of time and y of t. You can see this is very much like the 2 equations we just developed, of course, for the second and first order explicit Euler methods. It's a general form. We should think of the LTE, the local truncation error, as a residual, and it looks just like the residual which we discussed earlier, when the exact solution of the PDE and OD is evaluated. So you can imagine, of course, it's just like the residual in that the local truncation error will go to 0. With a numerical scheme, it will represent something a little bit different. It represents the truncation error when neglecting higher order terms. That's the local truncation error. Of course, it'll become smaller and smaller with the more and more higher order terms we add. So let's try and generalize this idea with our previous approaches and create something more general. We'll generalize this explicit scheme for higher order through the following argument for a particular second order scheme. So we'll introduce 2 constants, k1 and k2. k1 will be a part of the approximation of the new solution at higher time. We'll call that some delta t times f. This is exactly like the previous equations we've developed. Look at this delta t times f. Here's the delta t, and here's f. This is the higher order terms, which is local truncation error. Delta t, here's f. Now, the corresponding second order term, now we might have another k, and we would approximate this k as some f, the same right-hand side f with the same delta t, but we're taking time and the current solution at time I, and we're adding some alpha delta t and beta k1. So we're adding some coefficient. We're changing the time from, instead of just delta t, to some time plus alpha, which is usually pretty small, times delta t. Plus, of course, yi. This is some beta, which modifies and perturbs the solution about this value of yi, which is the currently known solution. Now, why do we do that? You'll see we actually are forming a system of equations. We might be able to optimize these coefficients. We can now insert these into our explicit marching scheme. They take the form of y of I plus 1 equals y of I, that's a new solution equals the old solution, plus a of k1 plus b of k2. A and b are now two different coefficients. So we now have a few different coefficients that we don't explicitly know. Alpha and beta, a and b. And it's our choice to choose these. You can imagine in certain choices, we recover the schemes we've just developed in this class. A to 1 and b to 0, we've recovered, of course, the explicit scheme. So this is a way to generalize all these different schemes with coefficients. We would optimize them to try and achieve the lowest local truncation error possible. By doing that, we would increase the order of accuracy of our scheme to an optimal value. This is the beauty of the RungeKutta scheme. Let's show how to do that. Well, we would actually do it with our old friend, the Taylor series or expansions, and we would use those to express the LTE for this particular type of scheme. Recall that K1 is delta t of f. We can't do much more with that now. K2 is delta t of f of t plus alpha delta t of y plus beta K1. We can then expand these particular terms of the arguments of K2 with a Taylor series. That's shown on this line. We can redefine now our LTE by inserting K1 and K2 with A and B definitions from the last equation on slide 9. That's what you're seeing here in the LTE equation. We then go through and make some assumptions to simplify it. You'll see, and of course a little bit of calculus, excuse me, and you'll see that when we now have an equation of 1 minus a minus b of f, which is the right-hand side function, plus 1/2 minus b alpha delta t f t, plus 1/2 minus b beta delta f y f plus higher order terms. So Drs. Runge and Kutta worked very hard to put the LTE in this form. Why did they do that? Well, you can see if we want the LTE to be 0, we would want the right hand to be very close to 0, if not 0 itself. Now it turns out, if you look carefully, if we want this term to be 0, we might think that, hey, we want 1 minus a minus b to be 0. So we could set a equals 1 minus b and insert it. This whole first term goes to 0, of course. Then we have these other terms, 1/2 minus b over alpha and 1/2 minus b over beta. I can make these terms 0 by simply setting alpha equals beta is 1 over 2 beta. This is the original RungeKutta scheme. For this order scheme, I can, for K1, K2, you can also imagine I have higher Ks, K3, K4, etc. But for K1, K2, this is the optimal scheme because, of course, I have let the LTE be 0 by definition. And I've chosen these four coefficients simply by making the LTE equal to 0. For some schemes, I might actually vary these to have other types of quantities and conserved quantities, for example, or maybe optimal schemes for RungeKutta. There's many of these. In fact, there's hundreds of types of RungeKutta time integration equations. You would have to explore these and find the right one for your particular computational fluid dynamics method. I encourage you to work through this mathematics itself. I try to show the steps here, and you won't fully understand it unless you try it, of course. Remember, mathematics is not a spectator sport. Let's now write down the so-called fourth-order RungeKutta scheme for computational fluid dynamics, or really any type of integration of differential equations or partial differential equations. It's really general. It's for any type of problem, but here we're applying to CFD. Let's look at the form now. Here we have K1, K2, K3, K4. We would write the y, the unknown variable at future time, at I plus 1 equals the variable at current time, plus, of course, the factor 1 over 6, which is the same for all constants. That's just like looking at these previous equations, say of a and b. Well, here we're setting them to, of course, 1 over 6 in every case. We've also defined K1 through K4 here. You can see it's an iterative approach. You can form a RungeKutta method of any order by just increasing the number of values at K. If we have 4 values of K, it turns out in this case that we have a fourth order scheme. For example, now K3 is nothing but delta t, which is always the same for every K, which is nice, of f of t plus 1/2 delta t and yi plus 1/2 K2. Now, in general, for a rth order RungeKutta scheme, we would need S evaluations of F for every time step. So if we have a fourth order scheme, we're actually evaluating the LTE equation 4 times. So if we want to increase our order, we would of course have to have more and more evaluations of the spatial discretization to find the residual or the LTE. That increases the computational expense. Or maybe not, because the RungeKutta scheme, because of its increasing order of accuracy, actually allows us to take larger and larger time steps per time step. So in a low order RungeKutta scheme, we can only take very small time steps. In a high order RungeKutta scheme, like fourth order or higher, we can take very large time steps, and both schemes will be stable. So there's a balance of the time step and how far we wish to advance in time with respect to the computational cost, of course. Down here, we've shown just a general rule. For R order schemes, R plus 1, and schemes greater than R plus 2, for instance, we have listed how many evaluations on the right-hand side we would need. This is a generally true expression. Let's now show a very simple example of the RungeKutta method. And we'll look at the same equation we looked at before for explicit Euler. Let's look at the continuity equation in 2 dimensions first, which is compressible. This should look familiar to you. We would first, of course, solve for the partial time derivative. So partial rho partial t, that's what the subscript t means when we're looking at PDEs, will be equal to negative of rho ux plus rho vy. Ux is partial u partial x, and v sub y is partial v partial y. We will set this middle term and define it as a residual, or LTE, in the RungeKutta framework. Now we can simply take this and set it to f in the previous equations. For a fourth order RungeKutta scheme, which has 4 time steps, we can rewrite the equations explicitly now. Here, r sup n is of course the residual at time step n. We can then substitute these in. You will note that we have unique residuals at the current time step, which we already know, and 3 additional ones we must calculate, of course. Why? Because R1 and R2 are at different time levels, and these time levels, you can see, are in these equations. For example, we would have to re-evaluate R at a different time level, technically, for example, at 1/2 t. We would then take these first 3 steps and insert them into the last step to find the explicit form, of course, of rho of n plus 1, which is the density of the new time level. We would also be performing these same operations on every other variable and equation. For example, a momentum equation, we would have, say, rho n plus 1, un plus 1 for the first momentum equation. The energy equation would have energy terms. We would apply these to all PDEs within the set of the differential equations. It might be good practice to try and program this yourself. If you're feeling a little bit lazy, you might just try the RungeKutta scheme in MATLAB and play with the different coefficients and order of accuracy, but you'll never learn as much as doing the mathematics yourself and then trying to program it explicitly in MATLAB. There's no other way to learn, and you'll never understand it unless you do it yourself. You have to do the work. Now let's look at a few explicit time integration examples. First, we'll look at the explicit Euler scheme. Let's read this together. This is from Chung's book. Use Euler's method to integrate y prime, that's partial y partial t, of 4 to the e 0.8t minus 0.5y from time of 0 to 4 with a time step of 1. So this means here's our differential equation that's first order ODE, nothing to do with CFD, from time 0 to 4. How do I do that? Well, I would need a delta time step. They're saying use the time step delta t of 1. And they'll say, and you need, recall, an initial condition. This is an initial condition problem where we're marching in time. At time 0, they're saying the solution y is 2. This is a direct boundary condition. Now you'll note that the exact solution can be determined analytically, of course, from the theory of ordinary differential equations. We won't review this, but you'll see that's right here. So we know the exact analytical solution. We want to find the numerical solution and compare it to the analytical solution to benchmark and make sure our numerical solution is correct and how accurate it is, what's the error, and how fast does it converge. This is nothing more than the explicit Euler scheme, shown here. Now, we have shown how to formulate this. We would basically add in y of n plus 1 minus y of n over delta t. Multiply both sides by delta t and add y of n to both sides. You'll find this equation. And then, of course, we fill in the values of delta t here. For example, we're taking a delta t of 1. So the left-hand side would have a value of t equals 1. The right-hand side is the initial condition. Y is 0, which we're given, which of course is 2. And the residual, or the LTE, will be the function of time 0 and y equals 2 times 1. So we can estimate and see from this particular equation that the slope at, say, time equals 0 is nothing but the residual of time equals 0. The original slope is approximately 3. That is what the function is actually evaluating here, right? Because, of course, dy dt is actually the slope of our particular function, right? It's explicitly given. That's the ODE. Therefore, we can insert these equations and find y of 1 equals 2 plus 3, 1 equals 5. So we've just done our first step from time equals 0 here to time equals 1, and we get a value of 5. The true solution at time equals 1 we can explicitly evaluate because we have the analytical solution in ODE. We would put in time equals 1 here and find a y value of 6.19. So our explicit Euler scheme from time 0 to 1, that's a time step, is not very accurate and is a huge error. The analytical solution has 6.19463. The numerical solution has a value of 5. This is rather troubling. We can calculate the error. We can take the analytical solution of 6.19463 minus our numerical solution of 5 divided by the analytical solution multiplied by 100 to get a percent error, and we see that we have a 19.28% error. That is very troubling. How can we improve the scheme? Well, we'll see that in a few minutes. We can also keep marching. For the second step, we would go from time 1 here to time 2. Notice our right-hand side equation is the same, but we have new values of t and, of course, y. New values of t. We can evaluate this equation with explicit Euler and get a value of 11.40216. We can also find the analytical solution. Chung was very nice to summarize these steps. For example, for this ODE, which we just defined with initial condition y equals 2 at time equals 0, we can go through and fill out the time equals 0 form. Y true represents the analytical solution in this second column. The first column represents the time from 0 to 4 seconds. Y Euler represents the numerical solution. The percent error is shown in the last column. We have explicitly shown the first time step. If you go through the process and go to the second, third, and fourth time step, you'll see eventually the analytical solution will be 75.33, etc., and the numerical solution will only be 56. So with the explicit Euler scheme, we have tremendous error which grows in time. In fact, solutions might diverge with this approach. On this graph, we've plotted the true solution, analytical solution with the numerical solution with time. The y-axis, of course, the value. You can see with increasing time steps, the analytical solution, which is the true, correct solution, and the numerical solution are diverging. How do we get a better solution? Well, the easiest way is simply to change the time step and make it smaller and smaller. Alternatively, we might try something else. And that would, of course, be increasing the order of the time integration scheme. Let's now do the exact same problem with the RungeKutta scheme with the fourth order. Let's read the problem again. We'll apply the fourth order RungeKutta method to integrate y prime equals 4 to the e to the 0.8t minus 0.5y from time 0 to 1 using a time step of 1 with y of 0 equals 2. So we would need to go back and look at our algorithm to understand this. Recall that this value is used to compute a value of y at a slope at a midpoint at first. So y of 0.5 will be 2 plus 3 of 0.5 is 3.5. We would then evaluate k2 from the RungeKutta method. Please go back and refer to those equations. I'll show them for a second. Now that you've seen the equations and made a note of them, we can try and continue to the next value of k. The slope, in turn, is used to compute another value of y. That's in practice physically how the RungeKutta method is using. And another slope at the midpoint will be y of 0.5 will be 2 plus 4.217299 at 0.5 equals 4.108649. You'll notice that the k2 form of the slope at the midpoint here at time 0.5, which is between time 0 and 1, is used in the next approximation for k3. We then do the slope approximation at the midterm point interval another time to find k4 in the equations. look at those again right here. Here's essentially K4. And we'll have y of 1 equals 2 plus 3.912974 times 1 equals 5.912974. You can see how we advance through this method. We're getting closer and closer to the analytical solution. Nonetheless, we can evaluate this and find K4. Remember, the equation will be the current time level, y, at time equals 0, with 1/6 of the addition of the coefficients K1 plus K2 plus K3 plus K4. We then put it in the final equation of the RungeKutta method, which is right here on slide 11. And we evaluate it. At time y of t equals 1, we'll then have 2 plus the right-hand side of phi, 4.201037 times the delta t, will be 6.201037. Let's now compare that with the analytical solution as we did before. If you go through that process and recall the analytical solution is 6.194631, you'll get an error of 0.103%. Relative to the explicit Eulers scheme, which has a 20% error, that's incredible in that only by using a higher order scheme with 2 time levels with midpoints, of course, a little bit more storage and work, we've decreased the error by basically what amounts to to over 2 orders of magnitude. I would also like to note that typically you are integrating systems of partial differential equations. It's worth showing the example here from Chung's book on integrating explicit systems using explicit Eulers scheme. So I encourage you to read through this example yourself. It's exactly like the previous examples, except now we have a simplified set of ODEs. Let's change directions now. We've talked at length about traditional explicit schemes that march in time. We'll talk about implicit schemes in a bit. But first, we need to talk about sub-iterations. Sub-iterations are shown in many contemporary CFD solvers, including ones that we'll look at this class. It is basically a time integration would benefit from placing an outer loop around the Melchering algorithm. So you would find perhaps a RungeKutta Method time integration scheme, and then we would have additional numerics that wrap around the particular solver. This reduces errors caused by the so-called convergence acceleration, especially for steady flows. This is rather confusing, and it'll be shown in practice, and it'll make much more sense. This will allow especially multidisciplinary solvers, such as error elasticity solvers, to be easily added to the code. So this is not required, but it's used to just accelerate the convergence of the solver, typically, especially for unsteady flows. So when we're selecting steady flows, we'll also have an option of understanding what the sub-iterations are. Let's try and understand this through a simple example of the 2D Euler equations. Here we've written them, once again, in vector form. Partial q partial t plus partial f partial x plus partial g partial y is 0. Here q is the field variables, densities, momentums, and energies. And f and g are the fluxes of q through surfaces of perhaps the finite volume or finite element scheme. Or this can also be written in a differential way. We've shown this vector form in the beginning of the class in fluid dynamics. Now, we might still discretize our operator, and we can use a discretization operator like this written in a general form. Here we have operating on q to advance it in time as its partial q partial t. 1 plus phi of q to the n plus 1 minus 1 plus 2 phi of qn plus phi of qn minus 1 over delta t. The fluxes and their discretization in space remain the same. You can see now we can, if we wish, find an explicit time marching approach using these equations. You have seen now we are at time levels n plus 1, n, and n minus 1, but we've done something very curious here. We've added time levels of n plus 1 instead of n at the fluxes. This is very much what we call an implicit scheme. Why is it implicit? Because we cannot explicitly solve for, say, q of n plus 1. We have unknown values F, G, and Q in the future. And so we would have to solve a system of equations to advance in time. This is not an explicit scheme. This is our first example of an implicit scheme. We have unknown values in the future, but we have a system of equations. How might we find and approximate the future values? Well, with a numerical method that uses an iterative technique. That's why they're called sub-iterations for advancing in time. Many contemporary CFD solvers use this instead of simply the explicit RungeKutta scheme itself or other time integration schemes. That doesn't mean that the most accurate and research-based schemes use sub-iterations. They don't. Sub-iterations are usually used more so in commercial solvers, and we can even try them out in our particular class if we wish to. We've also listed this new term phi, which we can change to, of course, find different schemes if we desire. Now, what we would do, we will replace the unknown time level n plus n with a sub-iterative value of p plus 1. We'll let p goes to infinity and define that q of p plus 1 goes to q of n plus 1 as p becomes larger. That's a sub-iteration. In sub-iteration solvers, the more iterations or sub-iterations you have from one time level to the next, or as you're going towards a steady solution, the more accurate solutions you'll, of course, have. We'll turn to our old friend, the Taylor series, and expand about the pth iteration when we make this substitution into our original form of the 2D Euler equations. Here for the fluxes, you'll have f of p plus 1 and g of p plus 1. They will be explicit formulas. And so we're explicitly marching over p for a large value of time levels to approximate those two flux terms. They're then put in, and we are explicitly marching in time after we perform, of course, the sub-iterations. Here we define delta q to p of p plus 1 minus q of p. We now combine all these operations and find a particular form, and we find 1 plus phi of q p plus 1 minus 1 plus 2 phi of q n minus phi q of n minus 1. Notice now we have an explicit scheme for p. The beauty of this is we've taken an implicit scheme, which inherently are more stable than explicit schemes, and turned it into an explicit scheme for p, which we let go to maybe 20 or 30 explicit iterations. Typically, most solvers use between 20 and 30 sub-iterations, but it's a variable that the user can completely choose. To finish the scheme, we would add and subtract QP to obtain and rearrange and find this final form. This is the kind of form that we would actually use in programming the solver. Here the right-hand side is actually the governing equations, and the left-hand side is the solver itself, which would be used to advance in time. We can illustrate the use of the solver through a little flowchart in the lower right. Recall we know time q to the n. That's the field variables, rho, velocities, pressures, temperatures, and energies at time n. We want to go to time n plus 1. To do that, we would go through the flow solver, which computes the delta q. Using the delta q, we would advance from p to p plus 1 and advance q to the p using delta q and p, q, p minus 1. So you can see we do have to store multiple levels, of course, q. We would then repeat this maybe 20 or 30 times. We can also track the residual or error of this process, and hopefully it goes to small values. We can then find the sub-iteration approach to go to steady flows, preferably in a very fast and implicit way, using a so-called explicit formulation. This is really beautiful, and it's used in many, many CFD solvers, especially true of commercial codes like Fluent and Star, and many others. It's also available in the codes we're looking in this class, but I encourage you to just try and learn for unsteady flows with explicit schemes. For steady flows, you're welcome to use these type of sub-iterations because they're going to help with convergence, acceleration, and stability. What we haven't talked about is the so-called current Friedrichs-Lewis CFL number. We will call this for now on the CFL number. It's named after their authors, of course. Courant was, of course, a famous mathematician. This is a team of folks who came up with this idea. You can think of it as the speed limit of computational fluid dynamics. That is, information in time cannot progress faster than the CFL number. This can be shown graphically, and I'll try and do this in one of our one-on-one class sessions. Now, for any particular time-dependent or steady flow solution algorithm, there's a limit on delta t. You can see that in the Euler example, which we just showed, we cannot set delta t to a very large value because the solution might be diverging and error becomes huge. So, if we set the value of delta t too small, we might have more accurate solutions, but it'll take us too long to get there. Optimally, we want to set delta t as large as possible while maintaining stability. The CFL number dictates and tells us what the maximum time step is for a particular simulation. We can set CFL number explicitly in solvers to find a delta t, or for study solvers to make the maximum step in time to find a solution quicker. CFL number must always be small and positive. Typically, the values could be anywhere like around unity. In my experience, it ranges maybe between 0.2 and 2 for explicit schemes. For implicit schemes, it might be anywhere from 1 or 10 or 1,000. It depends, and only with practice and understanding the particular solver and solution you're looking at will you be able to really find CFL numbers. CFL numbers themselves can be found analytically for simplified partial differential equations, or ODEs. This is really which comes back to stability analysis, which some people call the von Neumann analysis, named after John von Neumann. It's a numerical stability analysis for linear equations, which gives you the CFL number. If a CFL number is too large, then results in the solution will diverge. That means they'll go away and become infinity, or not a number, or something else. And that is true for both steady and unsteady simulations. So CFL number is critical. The CFL number is very simple, and we've written it down at the bottom of the slide. You can also see that it's very much a non-dimensional number. It has no units. CFL number, named after the authors, Courant, Fredericks, and Louis, goes as the local speed of sound times the time step, delta t, divided by the grid point spacing. There's actually many formulations and complicated forms of the CFL number. We would have to understand what they are to make progress, especially for particular solvers. But for now, just look at CFL number this way. It's the easiest and simplest way to think of it. And this is how we'll generally apply it in the class. If solvers are very complicated, it is impossible to find the explicit closed-form solution of a CFL number, or at least very, very difficult and impractical. In practice, it is found numerically through trial and error. That is, we know the grid is fixed, the grid point spacing is fixed. The speed of sound is a function of the physical problem. We can't really change c or delta x. We only have control over delta t. If we increase delta t, we increase CFL number. Alternatively, decrease delta t to maintain stability, we decrease it. You always want to have a large time step to get to your solution as fast as possible. Now, typically for other types of solvers, like a steady solver, we might fix the CFL number. We have c and delta x still fixed, and delta t would vary at different places in the grid. What does this mean? For steady solvers, delta t is different at different grid points depending on the grid point spacing and speed of sound c. It also has a very physical explanation. Think about wave propagation speeds with respect to t. You cannot violate the speed of information traveling at speed c. If information in the space-time travels faster than speed, in this case it's the speed of sound or speed of light if we're doing relativity, then we would break the law and break like the equivalent speed of light, but in the fluid dynamics problem at the speed of sound. This is the most simple and perhaps a little bit flawed analogy, but it's a great way to think about it if you're just learning about CFL numbers for the first time. Let's turn our attention to another methodology. We talked about explicit schemes at length. We talked about sub-iterations, but what happens when we form implicit schemes, which we've alluded to in the sub-iteration approach. Implicit schemes mean that we need to have and form a system of equations to advance in time instead of finding explicit forms. It's the opposite of the explicit method. We would need to find solutions at a future time using knowledge of the future time, present time, and perhaps past. So, to understand the future, we need to know something about the future and the present. This is very counterintuitive. Through this approach, we would have thankfully, restrictions on stability, and that typically implicit schemes are used because we can use larger time steps and they're much more stable than the explicit schemes. In fact, CFL number is not very important in implicit schemes because we cannot explicitly violate the CFL conditions. We will illustrate this through a simple example, and it applies to all more complicated partial differential equations. Consider the conservation of mass in 2 dimensions. We would have partial rho partial t plus partial rho u partial x partial rho v partial y. You can see, unfortunately, I've missed a plus between these 2 terms. I'll correct that in my notes. Now, we will discretize this equation with central differencing for the second and third term in space and first order differencing in time. Let's find out what we have. So for mass conservation, we can write using this methodology, rho of n plus 1 equals rho of n plus these phi terms, which I can let vary. We'll have on the right-hand side time levels n, n minus 1, and n. We'll also have the typical delta t's. We'll also have partial derivatives on the right at different time levels. But of course, the problem with this scheme is that we have time levels n plus 1. This is not good because we don't have an explicit form. We now have an equation which we would have to form and solve as a system of equations because we don't know rho of n plus 1. Now here we've redefined partial rho of t and partial rho of t at n and n plus 1 respectively. Here's the right side of these values. You'll see the first left-hand side is the typical explicit form, equal to the right of the current time level times these coefficients. Phi will be a constant, as you'll see in a second, which we set to recover schemes. Phi of n and phi of n minus 1 are here in the second term. So this whole first three terms in the equation represent a general scheme. Then we add in a delta t and average them over rho of n plus 1 and rho of n. See, phi delta t over 1 plus phi and delta t over 1 plus phi. We have partial rho n, partial t, and partial rho n plus 1 and partial t minus partial rho n partial t. Now, I've written it in this way, which is very complicated, but you'll see the advantage of this. We can set phi to recover any of the schemes which we've talked about, of course, except for higher order RungeKutta. If we, for example, set phi to 1/2, we would get a trapezoidal method. We can also vary phi to any value between 0 and 1 and recover all kinds of different integration methods. For example, trapezoidal refers to the order of accuracy and time integration that you would have found if you did a numerical integration using the trapezoidal rule. This is actually a brilliant approach, and it's of beam warming. The beam warming scheme is very interesting, and you can value these values of theta and phi respectively in these equations to find any of these types of first or second order integrations. They're all going to be implicit schemes. One is the classic implicit scheme of Euler, and the other two are more advanced, which are higher order. So you can see how the scheme varies with order on the right-hand side of this column of theta and phi. Here is the most classic Euler implicit scheme. Here we have rho of n plus 1 at ij equals rho of n of ij minus delta t, which is the residual on the right-hand side of the equations, which we discussed earlier, of the two central order finite difference stencils. And we've placed them at n plus 1. So you can see we would have to solve for this scheme all future values of rho and rho u. We would also have to do this to, of course, the Navier-Stokes momentum equations. That can be very difficult, of course. This is much more hard and difficult to program in a computer code, but the advantages are apparent in that we will gain tremendous stability of our solver and advance at very large delta t's. You can see in this particular equation, all that we know is delta x, the constants 2, the numbers 2, and the previous value of density. We don't know rho u at n plus 1 or any other grid points. Let's try a few more examples to really illustrate this. Let's look at it for, of course, the one-dimensional wave equation, which will illustrate an implicit scheme using first order. So recall the wave equation will be partial u partial t plus a, which is some speed of sound, times partial u partial x. That will be equal to 0. All this means is that the wave is going in one particular direction. I could also set negative and find an equivalent and interesting system. We would then discretize this with the implicit Euler approach. We would subtract both sides by a partial u partial x. Then we would discretize the left-hand side in respect to time. We would write u of n plus 1 minus u of n over delta t. See how that's discretized for the first term. We would then discretize the right-hand side of negative a over 2 delta x times the difference of u over the two grid points. Here we have a first order of accuracy scheme and right-hand side second order. There's the famous Craig-Nicholson method. If we modify this form to the one shown below, which is the implicit Euler scheme for the one-dimensional wave equation, we can also write it in a slightly different way. This is what two people did. Craig-Nicholson, who is another professor-student team. They wrote u of I n plus 1 minus u of I n over delta t, which is the same as the Euler implicit method, but now they've written the right-hand side as an average, essentially, an average of the spatial derivatives at the future time with respect to x and the present time. So they have increased through this methodology an essentially second order time and space scheme from what was originally a first order time and space scheme, just through this. How did they do this? They just simply made the substitution and proved mathematically that it results in a second order time accurate scheme. That's brilliant. The problem with this averaging technique is that, of course, it results in two time levels, n and n plus 1. This is a problem, of course, because now it's an implicit scheme. But the advantages are apparent. It is highly stable and one of the workhorses of contemporary fluid dynamics. Let's now make a few notes on the multi-step schemes. A multi-step time integration scheme will combine both the advantages from both the implicit and explicit scheme, so we can make a multi-step scheme which combines the two. The advantages here are, of course, we'll have better stability, convergence, and accuracy of our CFD solver, and they're usually improved with this multi-step approach between time levels n and n plus 1. There's many types of these schemes, and you'll see them if you take a graduate research course in CFD. Such schemes you might see in the future are called Richtmeier, Lex-Wendroff, and McCormick. These are all excellent examples of the so-called predictor-corrector schemes, which is a type of multi-step scheme. The most basic example is the Richtmeier multi-step scheme. These, of course, are named after their authors. Perhaps one day you'll come up with your own scheme which will be adapted by the community, and you too can have your name by the scheme. Wouldn't that be cool? In step 1, because it's a multi-step scheme, you can see we make an explicit time step for perhaps this particular discretized form of the equation, which is, its form is not too important. So, in step 1, we would have the explicit scheme. In step 2 is like a corrector scheme, and you can see we now have time levels n plus 1/2. That is the midpoint. It is the midpoint between times n and 1/2. The second part of the scheme is an implicit scheme. So the first step is an explicit scheme, the second step is implicit. We've created a lot of these schemes just through trial and error and a wonderful understanding of ordinary differential equations and numerical analysis. They have gone through and proved in their mathematical papers the stability characteristics for simple ODEs of these schemes and proved that they're stable. And they have improved accuracy and convergence, of course, and shown the test numerically. That is the characteristics and proof needed that a scheme is superior than perhaps other sources. One important scheme, of course, is the McCormick multi-step scheme. You'll see this works excellently for nonlinear problems. A lot of the discretizations we used earlier were for linear problems, but fluid dynamics is nonlinear. This is where a scheme like McCormick comes in. Let's just briefly review it so you know what the steps are. And you can, of course, try these with a simple ODE or nonlinear ODE if you so desire with MATLAB or a better programming language like Fortran or C. Here, once again, we take a step to an intermediate step, as McCormick wrote, as the star value, sup star, and it'll be related of u of I n plus 1/2. So the first step from at point I will be n plus 1/2 equals the right-hand side of 1/2 of u to the n to the un sup star. You can see this is actually trying to get to an intermediate step, but we can't really do this because the system isn't really closed. So step 1, if we break down this equation into two steps, will be u of I sup star minus u of I n over delta t, which is explicit, as you see, so we can explicitly find u of I sup star, that's a multi-step scheme, will go as a simple finite difference on the right. And this is formulated for the simple one-dimensional wave equation, which we showed earlier. We'll go to the second step, which is u of I n plus 1 minus u of I of n plus 1/2. Of course, n plus 1/2 is the intermediate step over delta t over 2 equals this form on the right-hand side. You're welcome to read more about these schemes in their original papers simply by pulling them through Google Scholar or through our library system. They're very deep, beautiful mathematical theories in discrete mathematics. But to really understand them and see their value, you'll have to spend a lot more time studying them. And of course, this is an introduction to CFD class. I'm just trying to get you to look at the schemes and how to understand them and implement them for now. The reasons that they are more stable and faster convergence should be just viewed for now as that they are implicit schemes and contain higher stability, but at, of course, a higher computational cost. You can always rewrite these types of schemes, the so-called predictor-corrector schemes, as a prediction step and a correction step. And of course, the McCormick scheme for these nonlinear problems has an order of second order in time and space. Let's now talk about what we did today. We have only explored the most basic concepts of implicit and explicit time marching schemes. Remember, implicit schemes are trying to find implicitly, that is, you can't write down the closed form equations for the future time, of multiple variables at multiple time levels. Explicit schemes are easier to program, and they might have just as good of accuracy. The advantage, of course, is that they're simpler. The methods are also numerous, and the choice of a method has a very large impact on its solution. A careful choice of an implicit scheme or explicit scheme and their orders is critical for CFD, and it always is going to be problem dependent. You have to choose the right time integration approach or steady state convergence approach for the problem at hand. We've also talked about steady versus unsteady flows, which are critical for choosing their particular solver. Remember, there generally is not a correct choice. So you will have to become very familiar with these schemes, and the only way to do that is to use them and maybe program them yourself if you so desire to understand them at a deeper level. And then you can be an excellent CFD practitioner. Next time, we're going to talk about particular algorithms for incompressible flow and compressible flow. These are much more complicated than the schemes we talked about today. But in almost all commercial CFD solvers, you'll have these choices of schemes, especially the ACM, piezo, and simple algorithms, which are for incompressible flows. For compressible flows, we would use the so-called piezo preconditioning or FDV technique. We'll talk about all these at length and how they work algorithmically. Of course, they're designed to find steady or unsteady flows at very, very fast convergence rates, and they're used heavily in industry. Thank you very much for your time today. I'm Professor Steve Miller.